Okay, so this is the last two things, and let's see if I can group them together and introduce them at the same time. So angular momentum is going to be called L, and I'll directly quote the vector version of it. So L vector is the angular momentum, and it's R cross P. Okay, so where did let me write this as well. And the rotational kinetic energy is 1/2 I omega squared, like this. So how do I know this? Is because remember we have Newton's second law is essentially the upgraded version, right? It's dp dt. Okay, so now what if I do r cross, let me apply a cross product. So I'll do r cross f, and this guy, this side I'll have r cross dp dt. Okay, so this is usually the radius of a rotation, right? So this is the position from the axis of rotation. Remember, r is displacement from the axis of rotation. So this will give you the torque, right? R cross F, the net torque. And that's not going to change, right? This is not going to be dependent on time. So this is just going to stay constant if it's a rotation. So this can go inside and outside of the derivative freely. Okay, so now it would be wise to call this a new name, like this. And if this is an angular force, this is an angular momentum, right? You have a linear force, linear momentum, and now basically just take a r cross product with r on the left. Remember, cross product depends on doing it from the left or the right, but we're going to do it on the left. This guy can go in. This is basically torque, and now you have this upgraded version of it. And you can, so that's where this comes from. And yeah, there is also, you can also relate that to the moment of inertia, because let's say what is the momentum of this guy, right? So if it's rotating like this, what's the speed? How does it relate to the angular acceleration of this mass? Let's say I have a point mass that's going to rotate around the axis like this. Okay, so remember the tangential speed is related to the angular speed this way. Why? Well, because theta is L over R, right? So d theta dt is, the R is not going to change, right? The L is the arc length. So this is the length it travels. This is the angle it travels. So if I see the rate of travel of this, so that's dl dt, that's basically the tangential velocity. So how much L you have moved per unit time. And this is how much theta you've moved, right? So the tangential velocity is omega times r, all right? So good, so that's how you can relate. And sometimes we don't need even to write this because there's no, if you go around here, the velocity is always sort of tangent to the path of motion. So so that's the velocity. So what's the momentum of this guy? The momentum is, again, in the tangent direction, right? It's mv, so that's m omega r, like that. So let's look at the magnitude of this, right? So if I just look at the magnitude, we'll worry about the direction in a second. The magnitude is rp sine theta, because cross product, and this is the included angle between here. So let's see. So r, p is m omega r. What's the sine theta? So the velocity is going this way, which means the momentum is also going this way. Okay, this is the displacement from the center. So what's this angle between r and p? Well, I can't compare it unless they are from the same point, right? So remember, from day one we said to make comparison between vectors, make sure they originate from the same point. whether you want to add them or subtract them, right? Yeah, so the angle between R and P is 90 degrees because R is the displacement from the, this is right, displacement from the axis of rotation, and P is the, it's proportional to V, right? So, so it's gonna go in the tangent direction. Yeah, I don't want a vector equaling a scalar, so I'm not going to put it here. That's just going to be a comment on the magnitude. Okay, so yeah, it's going this way, so it's 90 degrees. So this is going to be sine 90 degrees. Okay, so that's just 1, and I have m omega r squared. Okay, what can I, let me write this as mr square omega. And mr square is exactly the moment of inertia of the point mass, right? It's distance r away from the axis of rotation and mass. So you have the magnitude of the angular momentum is also equals to this. So this is a definition. And this is a formula for the magnitude, okay? So this is a formula for the magnitude. So be careful, there's a hierarchy over here. This is more important than this. But this is nice, I particularly like this, is because if you compare with the magnitude of the linear momentum, it has very nice parallel, right? This is the linear velocity, you have angular velocity. You have a linear inertia, you have a rotational inertia. You have linear momentum, you have angular momentum, okay? Yeah, I won't sort of justify where this comes from. It's essentially the same thing. You look at a kinetic energy and rearrange some of the symbols. But yeah, so we learned these two definitions. I'll find this as well. And maybe we'll look at just what we can apply this to get a better feel of these things. And that will wrap up all the things you need to learn. So these are sort of the last two key concepts and ingredients you will need. Okay. All right. So we'll see you in the next video.